Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are training a custom language model for your company using a large dataset. You plan to use the reduction server strategy on Vertex AI. You need to configure the worker pools of the distributed training job. What should you do? The options are: Option A, configure the machines of the first two worker pools to have GPUs, and to use a container image where your training code runs. Configure the third worker pool to have GPUs, and use the reduction server container image. Option B, configure the machines of the first two worker pools to have GPUs and to use a container image where your training code runs. Configure the third worker pool to use the reduction server container image without accelerators, and choose a machine type that prioritizes bandwidth. Option C, configure the machines of the first two worker pools to have TPUs and to use a container image where your training code runs. Configure the third worker pool without accelerators, and use the reduction server container image without accelerators, and choose a machine type that prioritizes bandwidth. Option D, configure the machines of the first two pools to have TPUs, and to use a container image where your training code runs. Configure the third pool to have TPUs, and use the reduction server container image.
To arrive at the correct answer, we focus on the keywords: reduction server strategy on Vertex AI, configure the worker pools.
The correct answer is option B, configure the machines of the first two worker pools to have GPUs and to use a container image where your training code runs. Configure the third worker pool to use the reduction server container image without accelerators, and choose a machine type that prioritizes bandwidth.
Why is this correct? B. Reduction server optimizes distributed training on GPUs. The third worker pool runs the server, which only needs high network bandwidth for routing and gradient accumulation, so it requires no accelerators. Why are the others incorrect? A. The third worker pool for the reduction server handles gradient accumulation and networking, so it does not require expensive GPUs. C. Reduction server is designed to optimize all reduce operations for GPU training, not TPUs, which have their own specialized high-speed interconnect. D. Reduction server is for optimizing GPU distributed training, not TPUs. Furthermore, the third worker pool does not require any accelerators.
Your organization manages an online message board. A few months ago, you discovered an increase in toxic language and bullying on the message board. You deployed an automated text classifier that flags certain comments as toxic or harmful. Now some users are reporting that benign comments referencing their religion are being misclassified as abusive. Upon further inspection, you find that your classifier's false positive rate is higher for comments that reference certain underrepresented religious groups. Your team has a limited budget and is already overextended. What should you do? The options are: Option A, add synthetic training data where those phrases are used in non-toxic ways. Option B, remove the model and replace it with human moderation. Option C, replace your model with a different text classifier. Option D, raise the threshold for comments to be considered toxic or harmful.
To arrive at the correct answer, we focus on the keywords: benign comments referencing their religion are being misclassified as abusive, false positive rate is higher for comments that reference certain underrepresented religious groups, limited budget, already overextended.
The correct answer is option A, add synthetic training data where those phrases are used in non-toxic ways.
Why is this correct? A. Adding synthetic data with these phrases in non-toxic contexts directly addresses the model's bias and reduces false positives efficiently, accommodating the limited budget and overextended team. Why are the others incorrect? B. Replacing the model with human moderation is extremely expensive and time-consuming, which directly contradicts the constraints of a limited budget and an overextended team. C. Building and deploying a completely new model is resource-intensive and might not solve the data-driven bias, making it unsuitable for a team with limited budget. D. Raising the overall threshold might reduce false positives but will increase false negatives, missing actual toxic comments, failing to specifically address the bias against these religious groups.
You are developing an ML model using a dataset with categorical input variables. You have randomly split half of the data into training and test sets. After applying one-hot encoding on the categorical variables in the training set, you discover that one categorical variable is missing from the test set. What should you do? The options are: Option A, use sparse representation in the test set. Option B, randomly redistribute the data, with 70% for the training set and 30% for the test set. Option C, apply one-hot encoding on the categorical variables in the test data. Option D, collect more data representing all categories.
To arrive at the correct answer, we focus on the keywords, categorical input variables, one-hot encoding on the categorical variables in the training set, one categorical variable is missing from the test set.
Correct answer is option C, apply one-hot encoding on the categorical variables in the test data.
Why is this correct? C. Pre-processing transformations applied to the training set, such as one-hot encoding, must also be applied to the test set to ensure the feature dimensions and input structure match what the model expects. Why are the others incorrect? A. Using a sparse representation only optimizes memory efficiency for zero-heavy matrices. It does not address the fundamental issue of aligning feature dimensions between training and test sets. B. Randomly redistributing the data with a different split ratio does not guarantee that all categories will be present in both sets and fails to address proper pre-processing alignment. D. Collecting more data is an unnecessary and resource-intensive step, as appropriate pre-processing and encoding pipelines can handle missing categories in test datasets.
You have been asked to productionize a proof-of-concept ML model built using Keras. The model was trained in a Jupyter notebook on a data scientist's local machine. The notebook contains a cell that performs data validation and a cell that performs model analysis. You need to orchestrate the steps contained in the notebook and automate the execution of these steps for weekly retraining. You expect much more training data in the future. You want your solution to take advantage of managed services while minimizing cost. What should you do? The options are: Option A, move the Jupyter notebook to a notebook's instance on the largest N2 machine type, and schedule the execution of the steps in the notebook's instance using Cloud Scheduler. Option B, write the code as a TensorFlow extended, TFX, pipeline orchestrated with Vertex AI pipelines. Use standard TFX components for data validation and model analysis, and use Vertex AI pipelines for model retraining. Option C, rewrite the steps in the Jupyter notebook as an Apache Spark job, and schedule the execution of the job on ephemeral Dataproc clusters using Cloud Scheduler. Option D, extract the steps contained in the Jupyter notebook as Python scripts, wrap each script in an Apache Airflow bash operator, and run the resulting directed acyclic graph, DAG, in Cloud Composer.
To arrive at the correct answer, we focus on the keywords, productionize, Keras, data validation, model analysis, orchestrate the steps, weekly retraining, much more training data in the future, managed services, minimizing cost.
The correct answer is option B, write the code as a TensorFlow extended, TFX, pipeline orchestrated with Vertex AI pipelines. Use standard TFX components for data validation and model analysis, and use Vertex AI pipelines for model retraining.
Why is this correct? B. TFX provides native production pipeline components for Keras models, including data validation and model analysis. Vertex AI Pipelines offers a fully managed, scalable, and cost-effective serverless environment to orchestrate these steps for automated weekly retraining on large datasets. Why are the others incorrect? A. Moving the notebook to a single large instance isn't scalable for growing data, lacks robust pipeline componentization, and isn't cost-effective as it is not a fully serverless orchestration approach. C. Rewriting the Keras-based workflow into Apache Spark is unnecessary, complex, and doesn't utilize standard ML components, leading to higher development effort and potential compatibility issues. Why are the others incorrect? D. While Cloud Composer orchestrates DAGs, wrapping scripts and bash operators ignores built-in ML components for validation and analysis. Additionally, Composer typically incurs higher baseline costs than serverless Vertex AI pipelines.
You are building an ML model to predict trends in the stock market based on a wide range of factors. While exploring the data, you notice that some features have a large range. You want to ensure that the features with the largest magnitude don't overfit the model. What should you do? The options are: Option A, standardize the data by transforming it with a logarithmic function. Option B, apply a principal component analysis, PCA, to minimize the effect of any particular feature. Option C, use a binning strategy to replace the magnitude of each feature with the appropriate bin number. Option D, normalize the data by scaling it to have values between 0 and 1.
To arrive at the correct answer, we focus on the keywords. Features have a large range. Features with the largest magnitude don't overfit.
The correct answer is option D, normalize the data by scaling it to have values between 0 and 1.
Why is this correct? D. Normalizing the data to a 0 to 1 range, min-max scaling, directly resolves magnitude disparity, ensuring large magnitude features do not disproportionately influence or overfit the model. Why are the others incorrect? A. Logarithmic transformations are typically used to handle skewed distributions, not to scale all features to a uniform, bounded range. B. PCA is used for dimensionality reduction and actually requires data to be scaled prior to application, otherwise large magnitude features will dominate the principal components. C. Binning discretizes continuous variables, resulting in a loss of valuable information and granularity that could be important for the model.
You built a custom ML model using scikit-learn. Training time is taking longer than expected. You decide to migrate your model to Vertex AI training, and you want to improve the model's training time. What should you try out first? The options are: Option A, migrate your model to TensorFlow and train it using Vertex AI training. Option B, train your model in a distributed mode using multiple compute engine VMs. Option C, train your model with DLVM images on Vertex AI, and ensure that your code utilizes NumPy and SciPy internal methods whenever possible. Option D, train your model using Vertex AI training with GPUs.
To arrive at the correct answer, we focus on the keywords: scikit-learn, Vertex AI training, improve the model's training time, try out first.
The correct answer is option C, train your model with DLVM images on Vertex AI, and ensure that your code utilizes NumPy and SciPy internal methods whenever possible.
Why is this correct? C. Scikit-learn relies on NumPy and SciPy. Deep Learning VM, DLVM, images include highly optimized math libraries, like Intel MKL. Leveraging these built-in optimizations speeds up CPU-based training significantly without requiring major code rewrites. Why are the others incorrect? A. Completely rewriting a scikit-learn model into TensorFlow requires significant developer effort and architectural changes, making it a poor first step. B. Standard scikit-learn does not natively support distributed training across multiple VMs without incorporating complex third-party frameworks like Dask. D. Scikit-learn does not natively support GPU acceleration. Provisioning GPUs for a standard scikit-learn script will just fall back to CPU execution, wasting resources.
You developed an ML model with AI platform, and you want to move it to production. You serve a few thousand queries per second and are experiencing latency issues. incoming requests are served by a load balancer that distributes them across multiple Kubeflow CPU-only pods running on Google Kubernetes Engine, GKE. Your goal is to improve the serving latency without changing the underlying infrastructure. What should you do? The options are: Option A, significantly increase the max_batch_size TensorFlow serving parameter. Option B, switch to the TensorFlow model server universal version of TensorFlow serving. Option C, significantly increase the max_include_batches TensorFlow serving parameter. Option D, recompile TensorFlow serving using the source to support CPU-specific optimizations. Instruct GKE to choose an appropriate baseline minimum CPU platform for serving nodes.
To arrive at the correct answer, we focus on the keywords CPU-only pods, improve the serving latency, without changing the underlying infrastructure.
The correct answer is option D, recompile TensorFlow serving using the source to support CPU-specific optimizations. Instruct GKE to choose an appropriate baseline minimum CPU platform for serving nodes.
Why is this correct? D. Recompiling TensorFlow serving from source enables advanced CPU-specific instructions, like AVX and FMA. Configuring GKE to use a matching baseline CPU platform leverages these optimizations to significantly reduce inference latency on CPU infrastructure. Why are the others incorrect? A. Increasing batch size improves overall throughput but degrades latency, because individual requests must wait longer for the batch to accumulate before being processed. B. The universal version of TensorFlow serving is explicitly compiled without advanced CPU optimizations for broad compatibility. Using it would likely worsen latency. C. Increasing the maximum in-queued batches allows the server to hold more pending requests, which increases queuing delay and worsens individual request latency.
You have trained a model on a dataset that required computationally expensive pre-processing operations. You need to execute the same pre-processing at prediction time. You deployed the model on AI platform for high-throughput online prediction. Which architecture should you use? The options are: Option A, validate the accuracy of the model that you trained on pre-processed data. Create a new model that uses the raw data and is available in real time. Deploy the new model onto AI platform for online prediction. Option B, send incoming prediction requests to a pub/subtopic. Transform the incoming data using a Dataflow job. Submit a prediction request to AI platform using the transformed data. Write the predictions to an outbound pub/sub queue. Option C, stream incoming prediction request data into Cloud Spanner. Create a view to abstract your pre-processing logic. Query the view every second for new records. Submit a prediction request to AI platform using the transformed data. Write the predictions to an outbound pub/sub queue. Option D, send incoming prediction requests to a pub/subtopic. Set up a cloud function that is triggered when messages are published to the pub/subtopic. Implement your pre-processing logic in the cloud function. Submit a prediction request to AI platform using the transformed data. Write the predictions to an outbound pub/sub queue.
To arrive at the correct answer, we focus on the keywords computationally expensive preprocessing, high throughput, online prediction.
Correct answer is option B, send incoming prediction requests to a pub/subtopic. Transform the incoming data using a Dataflow job. Submit a prediction request to AI platform using the transformed data. Write the predictions to an outbound pub/sub queue.
Why is this correct? B. Dataflow is optimized for high throughput, horizontally scalable stream processing. It effectively handles computationally expensive pre-processing in real time, integrating natively with pub/sub for ingestion and seamlessly calling AI platform for predictions. Why are the others incorrect? A. Training a completely new model on raw data abandons the required pre-processing steps, which is highly likely to degrade model accuracy and ignores the prompt's constraints. C. Polling a cloud spanner database view every second is a severe anti-pattern for streaming. It introduces unnecessary latency and overhead, and cannot efficiently scale for high-throughput workloads. D. Cloud functions are not designed for consistently high-throughput, computationally expensive operations due to strict CPU limits, execution timeouts, and cold starts, making Dataflow the superior choice.
You have created multiple versions of an ML model and have imported them to Vertex AI model registry. You want to perform A/B testing to identify the best performing model using the simplest approach. What should you do? The options are: Option A, split incoming traffic to distribute prediction requests among the versions. Monitor the performance of each version using Vertex AI's built-in monitoring tools. Option B, split incoming traffic among Google Kubernetes Engine (GKE) clusters and use Traffic Director to distribute prediction requests to different versions. Monitor the performance of each version using cloud monitoring. Option C, split incoming traffic to distribute prediction requests among the versions. Monitor the performance of each version using Looker Studio dashboards that compare logged data for each version. Option D, split incoming traffic among separate cloud run instances of deployed models. Monitor the performance of each version using cloud monitoring.
To arrive at the correct answer, we focus on the keywords: Vertex AI model registry, A/B testing, simplest approach.
The correct answer is option A, split incoming traffic to distribute prediction requests among the versions. Monitor the performance of each version using Vertex AI's built-in monitoring tools.
Why is this correct? A. Vertex AI endpoints natively support deploying multiple model versions and splitting traffic among them. Combining this feature with Vertex AI's built-in monitoring provides a fully managed, out-of-the-box solution, making it the simplest approach for A/B testing. Why are the others incorrect? B. Manually provisioning GKE clusters and configuring Traffic Director introduces massive operational overhead and infrastructure complexity, directly contradicting the requirement for the simplest approach. C. Building custom Looker Studio dashboards requires significant engineering effort to export, process, and visualize log data, which is far more complex than utilizing built-in monitoring. D. Deploying models to separate cloud run instances requires building custom deployment pipelines and manually configuring traffic routing, ignoring the ready-to-use capabilities of Vertex AI endpoints.
You work for a retail company. You have a managed tabular dataset in Vertex AI that contains sales data from 3 different stores. The dataset includes several features, such as store name and sale timestamp. You want to use the data to train a model that makes sales predictions for a new store that will open soon. You need to split the data between the training, validation, and test sets. What approach should you use to split the data? The options are: Option A, use Vertex AI manual split, using the store name feature to assign one store for each set. Option B, use Vertex AI default data split. Option C, use Vertex AI chronological split, and specify the sales timestamp feature as the time variable. Option D, use Vertex AI random split, assigning 70% of the rows to the training set, 10% to the validation set, and 20% to the test set.
To arrive at the correct answer, we focus on the keywords: tabular dataset, sale timestamp, sales predictions.
The correct answer is option C, use Vertex AI chronological split, and specify the sales timestamp feature as the time variable.
Why is this correct? C. Sales predictions inherently involve time series data. To prevent data leakage and accurately evaluate how the model predicts future events based on past data, you must split the dataset chronologically using the sales timestamp. Why are the others incorrect? A. Splitting by store name restricts training to only a single store's history, failing to capture the generalized temporal patterns across all stores required for a new location. B. The default data split typically assigns rows randomly. In time series forecasting, this causes data leakage by allowing future events to bleed into the training data. D. A random split ignores the temporal sequence of the sales data. This leads to data leakage, training on future information, and artificially inflates evaluation performance metrics.
You are responsible for managing and monitoring a Vertex AI model that is deployed in production. You want to automatically retrain the model when its performance deteriorates. What should you do? The options are: Option A, create a Vertex AI model monitoring job to track the model's performance with production data, and trigger retraining when specific metrics drop below predefined thresholds. Option B, collect feedback from end users, and retrain the model based on their assessment of its performance. Option C, configure a scheduled job to evaluate the model's performance on a static dataset, and retrain the model if the performance drops below predefined thresholds. Option D, use Vertex Explainable AI to analyze feature attributions and identify potential biases in the model. Retrain when significant shifts in feature importance or biases are detected.
To arrive at the correct answer, we focus on the keywords: monitoring a Vertex AI model, automatically retrain, performance deteriorates.
The correct answer is option A, create a Vertex AI model monitoring job to track the model's performance with production data, and trigger retraining when specific metrics drop below predefined thresholds.
Why is this correct? A. Vertex AI model monitoring is purpose-built to continuously analyze live production traffic for data drift and training serving skew. It can generate alerts when metrics breach defined thresholds, allowing you to automatically trigger retraining pipelines. Why are the others incorrect? B. Collecting and acting upon end-user feedback is a manual, subjective, and highly variable process, which completely violates the requirement to automatically retrain the model based on performance metrics. C. Evaluating the model on a static dataset will always yield identical results. It completely fails to measure how the model performs against evolving, real-world production data. D. Vertex Explainable AI focuses on interpreting individual predictions via feature attributions. It is not the native, automated service meant for detecting overall data distribution drift to trigger retraining workflows.
You are an AI engineer with an apparel retail company. The sales team has observed seasonal sales patterns over the past 5 to 6 years. The sales team analyzes and visualizes the weekly sales data stored in CSV files. You have been asked to estimate weekly sales for future seasons to optimize inventory and personnel workloads. You want to use the most efficient approach. What should you do? The options are: Option A, upload the files into cloud storage. Use Python to pre-process and load the tabular data into BigQuery. Use time series forecasting models to predict weekly sales. Option B, upload the files into cloud storage. Use Python to pre-process and load the tabular data into BigQuery. Train a logistic regression model by using BigQuery ML to predict each product's weekly sales as one of 3 categories: high, medium, or low. Option C, load the files into BigQuery. Pre-process data by using BigQuery SQL. Connect BigQuery to Looker. Create a Looker dashboard that shows weekly sales trends in real time and can slice and dice the data based on relevant filters. Option D, create a custom conversational application using Vertex AI Agent Builder. Include code that enables file upload functionality, and upload the files. Use few-shot prompting and retrieval augmented generation, RAG, to predict future sales trends by using the Gemini Large Language Model, LLM.
To arrive at the correct answer, we focus on the keywords: seasonal sales patterns, estimate weekly sales for future seasons, most efficient approach.
Correct answer is option A, upload the files into cloud storage. Use Python to pre-process and load the tabular data into BigQuery. Use time series forecasting models to predict weekly sales.
Why is this correct? A. Estimating continuous future sales based on historical seasonality is a classic time series forecasting problem. Loading the tabular data into BigQuery and applying dedicated time series models is the most efficient and statistically accurate method for this task. Why are the others incorrect? B. Logistic regression is a classification algorithm. The business requires precise numerical estimates for weekly sales to optimize inventory, not broad categorization into arbitrary high, medium, or low buckets. C. Building a Looker dashboard only allows the visualization of historical and current data. It entirely fails to satisfy the primary requirement of forecasting future sales. D. Large language models, LLMs, are optimized for text generation, not precise numerical time series extrapolation. Using an LLM for this task is highly inefficient, expensive, and prone to severe inaccuracies compared to dedicated statistical models.
You are building an ML model to predict customer churn for a subscription service. You have trained your model on Vertex AI using historical data and deployed it to a Vertex AI endpoint for real-time predictions. After a few weeks, you notice that the model's performance, measured by AUC, area under the ROC curve, has dropped significantly in production compared to its performance during training. How should you troubleshoot this problem? The options are: Option A, monitor the training/serving skew of feature values for requests sent to the endpoint. Option B, monitor the resource utilization of the endpoint, such as CPU and memory usage, to identify potential bottlenecks in performance. Option C, enable Vertex Explainable AI feature attribution to analyze model predictions and understand the impact of each feature on the model's predictions. Option D, monitor the latency of the endpoint to determine whether predictions are being served within the expected time frame.
To arrive at the correct answer, we focus on the keywords. Vertex AI using historical data, AUC, dropped significantly, performance during training.
The correct answer is option A, monitor the training/serving skew of feature values for requests sent to the endpoint.
Why is this correct? A. A degradation in statistical performance metrics like AUC typically indicates model decay caused by shifting data distributions. Monitoring training serving skew directly identifies if the live production data has drifted away from the baseline training data. Why are the others incorrect? B. Resource utilization metrics, CPU and memory, impact operational stability and throughput, but they have absolutely no effect on the statistical accuracy, AUC, of the model's predictions. C. Vertex Explainable AI highlights feature importance for individual predictions. It is used for interpretability, not for statistically measuring the data distribution drift between training and serving datasets that degrades AUC. D. Endpoint latency measures how fast the model returns a response. Serving speed is an operational metric that has zero mathematical bearing on the predictive accuracy of the model.
You need to train an XGBoost model on a small dataset. Your training code requires custom dependencies. You need to set up a Vertex AI custom training job. You want to minimize the startup time of the training job while following Google recommended practices. What should you do? The options are: Option A, create a custom container that includes the data and the custom dependencies. In your training application, load the data into a Pandas data frame and train the model. Option B, store the data in a cloud storage bucket and use the XGBoost pre-built custom container to run your training application. Create a Python source distribution that installs the custom dependencies at runtime. In your training application, read the data from cloud storage and train the model. Option C, use the XGBoost pre-built custom container. Create a Python source distribution that includes the data and installs the custom dependencies at runtime. In your training application, load the data into a Pandas data frame and train the model. Option D, store the data in a cloud storage bucket and create a custom container with your training application and its custom dependencies. In your training application, read the data from cloud storage and train the model.
To arrive at the correct answer, we focus on the keywords: custom dependencies, Vertex AI custom training job, minimize the startup time, Google recommended practices.
The correct answer is option D, store the data in a cloud storage bucket, and create a custom container with your training application and its custom dependencies. In your training application, read the data from cloud storage and train the model.
Why is this correct? D. Baking custom dependencies into a custom container at build time completely eliminates the overhead of installing them at runtime, drastically minimizing job startup time. Storing data in cloud storage instead of the container follows best practices for decoupling data from code. Why are the others incorrect? A. Hardcoding data directly into a custom container image is a major anti-pattern. Code and data must be kept separate to ensure flexibility, security, and maintainability. B. Installing custom dependencies dynamically at runtime via a Python source distribution forces the job to download and build packages every time it starts, significantly inflating startup time. C. This approach combines two severe anti-patterns: bundling data into the source code distribution and installing dependencies at runtime. This results in bloated code packages and extremely slow job startups.
You are developing a model to detect fraudulent credit card transactions. You need to prioritize detection, because missing even one fraudulent transaction could severely impact the credit card holder. You used AutoML to train a model on users' profile information and credit card transaction data. After training the initial model, you notice that the model is failing to detect many fraudulent transactions. How should you increase the number of fraudulent transactions that are detected? The options are: Option A, add more non-fraudulent examples to the training set. Option B, reduce the maximum number of node hours for training. Option C, increase the probability threshold to classify a fraudulent transaction. Option D, decrease the probability threshold to classify a fraudulent transaction.
To arrive at the correct answer, we focus on the keywords: prioritize detection, failing to detect many fraudulent transactions, increase the number of fraudulent transactions that are detected.
The correct answer is option D, decrease the probability threshold to classify a fraudulent transaction.
Why is this correct? D. To prioritize detection and catch more fraudulent transactions, maximizing recall, you must decrease the probability threshold. This forces the model to flag transactions as fraudulent even at lower confidence levels, drastically reducing missed frauds, false negatives. Why are the others incorrect? A. Adding more non-fraudulent examples worsens class imbalance. This biases the model toward predicting the negative class, causing it to miss even more fraudulent transactions. B. Reducing node hours prematurely cuts off the model's training time, which generally degrades overall predictive accuracy rather than specifically improving the recall of the positive class. C. Increasing the probability threshold requires the model to be more confident before predicting fraud. This results in fewer detections, directly contradicting the goal of catching more fraudulent transactions.